Good afternoon, everyone. Thanks for coming and thanks for staying. Today I am presenting our work, a measurement study on collision threat inside the cloud. Entering the era of cloud computing, more and more users are moved into cloud, making the cloud a tempting target. In the perspective of an attacker, the cloud can host many valuable targets, such as banking, medical services, some sensitive enterprise information, and even the business competitor. As a result, more and more attacks are launched towards the cloud. What makes the situation even worse is that in a public cloud, since everyone can become a user, including the attackers themselves, which means the attacker can launch attacks from inside the cloud. And such attacks from inside the cloud can leverage on more victim information and exploit more attack vectors, be more stealthy, and therefore causing more damage. One of the security problems from inside the cloud is so-called co-residence threat. Co-residence here is defined that in a public multi-tenant cloud, virtual machines belong to different users can be located in the same physical area. There are various attacks derived from such co-residence at a machine level, where the attacker virtual machine and the victim virtual machine are located on the same physical machine, and the attacker can launch attacks such as covert channel or side channel attacks. In the covert channel threat model, the attacker needs to control the victim and make the two parties communicate through unintended system channels such as L3 cache or memory bus. And the side channel is a more serious problem because the attacker does not need to control the victim, but can steal information through those unintended channels. Besides such machine-level co-residence, we also have rack-level co-residence, where the attacker deploys attack instances under the same rack with the victim. And there are also attacks derived from the rack-level co-residence, such as power attack, in which threat model, the attacker tries to deploy many attack instances under the same rack and increase the power consumption of the servers simultaneously to try to cheaper the circuit breaker of this rack. To understand such co-residence threat inside the cloud, on one hand, we wanted to understand over those years how cloud vendors have changed their cloud management policies and the impact on such co-residence threat. And on the other hand, we also wanted to understand as the attacker how one can upgrade his weapon to exploit some new attack vectors to launch new attacks. Therefore, we performed a systematic measurement study in a public cloud and to quantify the co-residence threat. And we investigate into the changes of the cloud management policies made by cloud vendors, including the virtual machine placement policy, the networking management policy, and the newly introduced defensive service, such as virtual private cloud. And we studied the impact on the co-residence threat. In our work, we choose Amazon EC2 as our particular study candidate because it is the pioneer of IaaS and it has the largest business scale. And since most business, the majority business of EC2 are held in the North Virginia data centers, we will focus on this part of the cloud, which is also widely known as US East region. In EC2, each instance has a certain type, such as T1.micro, M1.small, or M3.large. And such type will reflect the size or say the computational power of the instance. And the prefix, such as T1, M1, or M3, will indicate the model of the physical machine that hosts the instance. In EC2, there is also a concept called availability zone, which is basically a logical partition of the cloud. To begin with, we first quantified the co-residence threat inside of EC2. Namely, we wanted to find out how much effort an attacker needs to pay to achieve co-residence in the environment. And first, we wanted to see how much effort is required for the attacker to get a random pair of instances located on the same physical machine. And the following figures shows the number of probing instances required to launch, the actual money cost, and the time taken to achieve a random pair of instances on the same physical machine. And the figures also show the statistics for different types of instances in different zones. And as we can see in the default EC2 networks, it is not very easy to achieve coresidence. An attacker might need more than 200 probing instances to get a random pair of instances on the same physical machine. In a more real-world-like scenario, an attacker needs to place the attacker instance on the same physical machine with one particular target. So we also quantified such a scenario, and the following figures show how many probing instances, the money cost, and the time taken to achieve coresidence with one particular target. And as we can see, the attacker needs around 200 to 300 probing instances to achieve such coresidence. Besides such coresidence on machine level, we also quantified the rack level coresidence. In the threat model of power attack, the attacker tries to deploy as many attacker instances as possible under the same rack. So we quantified how many probing instances are required to place a certain number of instances under the same rack. And as this figure shows, the attacker needs around 500 probing instances to place 20 instances under the same rack. Note here, different from the work presented by the last talker, here we use some more like an old-fashioned way to achieve the coresidence. We did not explore some new, more fancy like a way to achieve coresidence because we wanted to give a more fair comparison with some results from previous works. In 2008, as we can see, it was extremely easy to achieve coresidence. With only 40 instances deployed, we can achieve 7 or 8 pairs of coresidence ones. And in 2012, another study claimed that on average, they can get 2 random coresidence pairs with around 160 probing instances. And in contrast, in our work, the attacker needs more than 200 probing instances to achieve such coresidence, and with the similar attack procedure. Such comparison means that achieving coresidence in EC2 has become more and more difficult. So we wanted to further investigate into the reason behind such observation, and we wanted to study the changes in the management policies of EC2. First thing we will look into is the virtual machine placement policy. As we find, which is also the most intuitive, currently EC2 has a much larger pool. Back in 2008, the study only observed 87 distinct physical machines that hosted the M1.small type of instances. In contrast, in our measurement, we can observe more than 600 physical machines that are hosting the same type of instance. Such a larger pool means EC2 has more choices to place an incoming instance, which will reduce the possibility of coresidence. And besides such a larger pool, we also find that the placement locality is heavily reduced. Placement locality means the relationship between the physical location of an instance and the properties of the instance, such as the instance type. After randomly sampling some instances with different types, we are able to draw this figure to show the relationship between the instance type and the private IP addresses of the instance. Since the private IP address is proved to be a strong indication of the physical location of the instance, so we can think the position of the node in this figure as a strong indication of the physical location of an instance in the cloud. And similarly, back in 2008, Similar experiments were conducted. And if we compare those two figures, we can see that the nodes in the figures from 2008 with the same type are grouped more tightly close to each other, which means that the type locality back in 2008 was much stronger. Similarly, we also investigated the zone locality. Before a user launches an instance, he will be asked to select a preferred availability zone. And we wanted to see whether this selection will impact the physical location of the instance. And similarly, we have results from our work, and we also have results from a study back in 2008. And again, if we compare these two figures, we can easily find that the availability zone locality back in 2008 was much stronger. And those reduced placement locality means that the virtual machine placement policy of EC2 might have introduced more randomness. And furthermore, we have observed that the virtual machine placement policy might have become more dynamic. First, we have observed very frequent changes in the mappings between public IP addresses and private IP addresses in EC2. And we even observed that instances with different types are placed on the same physical machine. Although this is still a very rare case, according to previous works, this had never happened before. Besides those changes in the virtual machine placement policies, we also investigated the networking management policy because the networking information is heavily used during the process of correlation attacks. And through a series of networking probings, we are able to collect many traces and analyze the potential changes in networking management of EC2. First, the most obvious change is that the domain 0 information is no longer available in EC2. Domain 0 is the privileged domain of Zhang hypervisor system, which is currently used by EC2. And since all traffic of an instance will go through this privileged domain, so this information was used by the attacker to uniquely identify the physical machine that hosts a certain instance. And therefore, by hiding such information, it will make the attack more difficult to verify the physical location of a target, therefore increasing the difficulty of correlation attack. Moreover, we also find that there are many important hops around the routing paths are hidden or obscured by EC2. First, back in 2013, a study claimed that all routing paths in EC2 had an even number of hops. And in contrast, in our work, we found that more than 34% of those paths become odd number of hops. And such change can indicate that it is possible some important routers and switches may not even appear along the routing path anymore. Furthermore, in our collected traces, more than 76% of the paths have at least one hop obscured. And such hidden and obscured routing information will make the cloud cartography, therefore the correlation attack, much more difficult. Besides the changes in those routing configurations, we also wanted to explore the networking topology because it is very important to rack-level correlations. Here, we are able to propose a faster algorithm to identify in EC2 whether two instances are located under the same rack and whether this rack is connected by the top-of-rack switch topology or other topologies such as end-of-row topology. In the TOR topology, each rack of server will be connected by a top-of-rack switch. And we randomly sampling some instances with different types in EC2. And overall, we identified 109 distinct racks. And our classification results suggest that the TOR topology is the dominating topology in EC2, and it has become the trend. Unfortunately, the TOR topology will be more vulnerable to rack-level collisions attack because the TOR switch itself can easily expose which rack is hosting the particular instance. At last, we investigate a very strong weapon of EC2, the virtual private cloud. VPC is a defensive service proposed by EC2 to provide the tenant an isolated networking environment. And by hiding most of the networking information, it has made the older way to achieve collisions impossible in VPC. And according to our measurement, VPC has already been widely used inside EC2. However, although VPC isolates the networking environment, it does not physically isolate those instances. So in theory, collisions is still possible. And however, VPC has indeed given the attacker a great challenge because the networking information is very limited. Without any private IP address, the attacker can no longer use the older way to achieve collisions as the previous works. And even the routing information related to the VPC instances will always hide some sensitive information to hide the physical location of the target. However, here we are able to propose a new way to achieve collisions in VPC by leveraging on the end-to-end latency and the number of routing hops. The first step, we use latency pattern to speculate the type and availability zone of a particular target. Here is a piece of so-called latency table we have congested. Each column stands for an anchor instance we have deployed in EC2 with certain types in different zones. And each row here stands for an instance in VPC with a certain type and in a certain zone. And each row of values will become a so-called latency vector. And after we get a target, we can perform the latency measurement from those anchor instances to this target to get a target latency vector and perform the similarity comparison to those baseline latency vectors. And we can choose the one with the highest similarity, and we can speculate the type and the zone accordingly. And our evaluation shows that such speculation can achieve an accuracy of 78%. After speculating the type and zone of a target, the attacker should launch the probing instances with the same type in the same zone. And then the attacker can apply two steps of filtering techniques. The first step is to leverage on the number of routing hops. If a probing instance and the target instance have different number of hops towards our anchor instances, then the probing instance is impossible to be located on the same physical machine with our target. And this step will filter out more than 60% of the candidates. And for the rest one, we will set up a latency threshold to filter out those ones with high latency. And this step, in fact, can filter most of the rest candidates. And in our experiments, we finally use covert channel to verify the collisions. And the results suggest that even with such covert channel verification, after the type and zone speculation and the two steps of filtering, the attacker can achieve a confidence around 70% that the rest probing instances are located on the same physical machine with the target. And of course, we have already known from the last talk, we can get some new techniques to perform the final step of collisions verification. And this figure shows with our approach how many probing instances are required to achieve collisions with a particular target in VPC by knowing its public IP address. And such results suggest that VPC indeed makes the collisions much more difficult. And on the other hand, such results also suggest that even with the VPC, correlation threat has not been eliminated yet. Therefore, according to our measurement and our analysis, we propose several ways to better defend against the correlations. First, the DNS system of the cloud should be protected better. Maybe can consider to introduce some randomness. Because in our study, we have used the DNS system of EC2 to quickly probing the cloud from inside and achieve the information of the victim. If the DNS system can introduce some randomness, such probing will no longer be possible. And it is also controversial to publish all public IP address ranges, such as EC2 does, because this can help an attacker easily scan the entire cloud. And some important routing information, such as the TOR switch information, should be protected better. And the virtual machine placement policy may consider to introduce more dynamics, such as leveraging the historical information of a user. So in conclusion, in our study, we have investigated Amazon EC2 to study the changes in the cloud management policies and the potential impact on correlations. And our study also suggests that even with all those management adjustment and the newly introduced defensive services, correlations threat has not been eliminated yet. So this ends my talk. I'm ready for any question. Thank you.
Thanks to the efficiency of all of our presenters, we have 17 minutes for questions. So.
Oh my God.
Any jokes? No. So have you considered the when you were doing these tests? How much did it end up costing? Because it seems as though when the medium instances seem like they start adding up fast when you end up with a bunch of them, and if you're using the same sort of techniques that from 2009, then you're going to have an awful lot of probes. So what's the economics of these sorts of attacks with your methodology?
I beg your pardon. The last of the question.
So you have to the cost of launching the number of probes in order to achieve co-residence. Do you have a sense of what those numbers look like? So how much would it cost for me to launch an attack against, say, a micro instance versus a medium instance, etc.?
Yeah, of course. We find that the number of probing instances, like for different types, they don't show like a very like a different pattern. However, the cost, of course, because like those public cloud, they always use pay as you go, and the money cost will be dependent on the size of the virtual machine. So of course, it will cost you more money to achieve correlations with a medium or large instance than a micro instance.
And you had mentioned potential mitigations, things like randomizing the space. Do you foresee that co-residence is still going to be an issue 6 years from now, or are there things that can fundamentally be done to eliminate the problem, or is it something that we're always going to have as a potential vector?
Basically, I don't think like this problem can be totally eliminated in a short time, because the problem is always there, and even with the VPC, we can say we always have various ways to achieve the correlations. But of course, as we can also see, the cloud vendors have paid lots of efforts to enhance the security. So I believe that the threat will be mitigated significantly. And
one more question. So you focused on EC2 in the previous talk, considered Azure and Google Compute Engine as well. How portable do you think your methodology is to other cloud environments?
I think the reason why we chose EC2 as our only study candidate is because first we don't have anything in Amazon, in Azure or Google or space for us to compare. So we are like, because we focus on the evolution of the management in cloud, so we will focus on EC2. But I think similarly, like maybe in some time later, like because currently now we have the results from other clouds, so maybe in the future, like some studies will like further compare like in other clouds.
This is not more of a question for you, but for the audience. We didn't really get the co-authors. We didn't really get a chance to too much chance into comparing and differentiating these two works. These two works are complementary in multiple ways. For example, they looked at older generations instances, and for example, they looked at T1.micro and M1, M4, and we looked at T2.small, which is newer ones, which is one of the important distinctions, and these are different hosts themselves. So it's more of a complementary study, and probably in the future we could get we could put up a document that actually differentiates and compares these two things, so that it helps the readers, because it's we didn't really have much space in both of our works to compare and contrast to each of theirs. So yeah, if you have any questions, please mail us. Yeah.
And also I want to mention that the ways to launch an attack in VPC, because both of our works like have performed the study like in this environment, but like as he said, like our works are mostly complementary, because like in his work, like he proposes like how to better exploit the placement strategies in the cloud to achieve a higher like possibility of collisions, and how to perform the collisions detection without the any like a cooperative technique such as covert channel. And I think our work, on the other hand, provides the heuristic to how to like speculate the type and the zone of the target, because this step is a prerequisite of launching collisions attack, as they studied in their work. Okay, thank you.
If there are no other questions, then we're going to have Zhang stand here awkwardly for the next 10 minutes until the session is over. Okay. Thanks, Zhang.